Okay, everyone. Now, I'm glad that we have this follow-up because not topic 9.10, so understanding when Q increases or decreases, and then describe the relationship between Q and the voltaic cell potential. Like, we kind of ended class last time with this, and there was a bit of a struggle, so I'm happy that we're coming back and we're addressing this idea. All right? So we saw last time that we were comparing E cell not at standard versus E cell at standard. Okay, and it has the little circle, the not, and that was minus, and then I don't even remember the exact one. Let me grab blue paper. I'll show you right where it's at so you'll know where it's at as well. And it's thermodynamics, electrochemical, and I'm talking about this one. So I have this little RT over NF. And then the most important part is the natural log of Q. So we have E cell minus RT over NF natural log of Q. Now, I don't want you to worry about this part. I want you to really think like this is just a positive number, okay? Like that's just some positive value, and we're gonna see when Q is greater than 1, less than 1, like what's going on here. And again, this was discussed in class, but we were looking at starting with the standard, okay? And one of the things that is standard is when the concentrations are 1 molarity. All right. So I can have a redox reaction, right, where it is gaining and losing electrons, and this happens in electrochemical cells. And we saw, and we wrote this down a lot, and I write it. As soon as I see that it's a battery that I'm talking about, I have my Leo the lion says GR, and then reduction, or red cat, cathode. Reduction happens at the cathode. Anox, anode is oxidation. So I have this metal, A, and it's becoming a 2+. So we went from neutral, like a 0, an oxidation number of 0, to an oxidation number of +2. So we are losing electrons, so this is oxidizing. So this is my anode. That's my anode, so this is my anode ion, right? And then if we look at B, we went from 2+ to 0. We gained electrons. This is reducing. So this is my cathode. That's the ion for the cathode, and this is the solid metal for the cathode. Okay? So I have my anode, cathode, anode, cathode. And if I were to write a Q expression or a K expression, I don't include the solids or liquids, but I would include the aqueous, and it would be products over reactants. It would be this A over this Q. Now, to simplify this, so you can always use this, it's going to be the anode ion, the concentration of those anode ions divided by the concentration of the cathode ions. Now it'll work for whatever equation you're wanting, okay? And we discussed, well, when these are equal, if it's a standard cell, and these are both 1 molarity, so concentration of 1 divided by concentration of 1 is equal to 1. That is when Q is equal to 1. Let's write 3 of these down. Again, we had them in the notes, but I want to do it one more time. Let's say that the concentration of the anode ion is equal to the concentration of the cathode ion. Okay? They're equal to each other. Well, if that's the case, maybe it's 1 and 1, 0.5 and 0.5, Q would equal 1. This would cause the natural log of Q. Maybe we need to add that to help us. The natural log of Q is going to equal 0. Okay? Anytime, and we plug it in. if we ever forget this, use your calculator. If I take the natural log of 1, it's going to be 0. So if this is 0, anything multiplied by 0 would be 0. So this whole thing is going to be 0. So this E cell, this battery that's different than what it was before, the voltage is going to stay the same. The cell potential is going to stay the same because we're minusing 0. So this new voltage is equal to what it was in its standard form, what it was before. Now let's change it. What if we either increase the concentration of the anode ion or we decrease the concentration of the cathode ion? And again, not moles, but concentration. So that would mean that we have a larger concentration of the anode or a smaller amount of our cathode. And that would result in a Q value that is bigger than 1. Q would be some number larger than 1. Okay? What if I take the natural log of a Q value that is bigger than 1? It doesn't matter what I plug in, it's just some value bigger than 1. Do you see how it gives me a positive number? That the natural log of a value that is larger than 1 is some positive number. Okay? Well, all right. If this is a positive number and this is a positive number, so a positive number times by a positive number, we have another positive number. And this new battery is going to have a voltage of the original battery minus some positive number. So that would mean that this new battery is got less voltage than the old battery at that standard. So when the anode outweighs the cathode as far as concentrations go, then the cell potential decreases. Now what if it's the opposite from this? So what if anode ion, what if we decrease the anode ion and or increase the cathode ion? Not the solid, but the ion floating in the solution. So that would result in smaller number, bigger number, so Q would be less than 1. Not 0, but less than 1. So Q would be less than 1. And if I plug in the natural log of some number, log or natural log, but let's do natural log of some number less than 1, like 0.5, I will get a negative value. So this will result in a negative number. Okay? If this number is negative and I multiply it by a positive number, this whole thing will become negative. And then if I minus a negative, that makes this positive. So this new battery would have a voltage that's higher than the old battery. Now, maybe we need to simplify it to help us memorize this. What about this? If we have more cats, because remember red cat and ox, so overall positive would be having more cats than ox. Okay, like you're a cat person in this scenario, like yes, give me more cats and I don't want any ox. And that's a positive thing. I would have a higher voltage. But if I have more oxen than I do cats, that's going to be a negative thing, and my cell voltage is going to go down. If they're equal, then so be it. I'll stay where I was at before. I didn't gain or lose anything. Okay, we're on to page 26. This is just a summary of what we were just talking about there. And so if we have, and honestly, I think we're going to leave this one. This is exactly what we just talked about, and it's just comparing, like, what if we add some of this, what if we remove some of this, and what if we add some of that. And we can see here that if we add this, then Q would be a smaller value. And we saw that that would result in a negative. Natural log of Q would be negative. And overall, because it's a double negative, because it's minus that negative, that our E cell would be bigger than the standard. So we'd have an E cell that would have a larger voltage than the standard. Okay. Now, what about this one? What if we remove some of the copper? So this is going to decrease down here. Okay. So let's do an example to help us. Like, what if I have 2 over 2? Like, let's just say it was before. 2 over 2, right? That equals 1. And then we're going to reduce some of this. So then it's a 2 over 1. When you reduce the numerator, it actually makes the whole value larger. So this would mean that our Q value is greater than 1. And we saw that when the Q value is greater than 1, this would result in a positive number right here, and we'd be minusing this positive number, so that our E cell is not performing as well. This new battery would have a smaller voltage than it was before, than the standard. Okay, great. Now, what about this one? We're adding some of this. So same as before, that would make Q bigger, and so then we saw that has the opposite effect on our E cell. So our E cell would be lower voltage than what it was before. Great. And last one, what if we remove some of this? This makes Q smaller. That would, the cell and the Q values are inversely proportional. So like if Q gets smaller, then E gets bigger. This new battery would have a higher voltage than the old one. All right, and then this is just a summary of that. And we'll get some practice on this in class. I want to keep going, and this is the only new concept for today. So current, I, current, and then we have this Q over T, okay, and Q is representing the charge. Now, understandably confusing, so we have to really pay attention. We had Q heat, but then look, Q charge. And when it comes to current, Q is representing the charge, okay? So it's the charge, and it has units of coulombs. And then we have T, which is time, specifically in seconds. And that's what an amp is, like units of amps, which I will have units of amps. This is coulombs per second, okay? So, with that in mind, it's like how many charges, even like electrons, flow past a given point every second. It's the charge per second. Like that's what our current is. The amount of charge that passes through a section, like a gate, like this point, per second, okay? So how much charge passes through the cross-section of a wire that is carrying 0.98 amps of current for 12.3 minutes? And then we need to figure out after that how many moles of electrons this is. And I actually can do this all at once, so let me help you figure that. Well, let's separate them. So we know that the current, our amps, is 0.987 amps, okay? And we know that our time is 12.3 minutes, but we need seconds. 12.3 minutes, and each of those minutes have 60 seconds. And so this is 738 seconds. And we are going to need the charge, okay? This Q value, that's what I'm going to solve for right now. So current is equal to Q over time. Time times by the current equals Q. So through 738 seconds times by 0.987 equals 738 728.406 coulombs of charge. Great, but how many moles of electrons is that? 728.406 coulombs. Well, guess what? We have a really cool conversion right here, that 1 mole of electrons is the same as 96,485 coulombs of charge. So coulombs, and we want to end with moles of electrons. So that's going to go right up there. And we have 96,485 coulombs per mole. So if I take this and I divide those coulombs, then we are only had 0.00, now let's see, sig figs at this point. Those were 3 sig figs, so 0.0755 moles of electrons. All right, nice. Let's end by doing one example, and then we'll get some practice when we're in class. How long will it take to plate out 3.56 grams of silver from a solution containing Ag plus ions when a current of 2.5 amps is applied? All right, so 3.56 grams of silver. That's what I'm starting with right now. Grams of silver, let's move to moles of silver. And I could go right from moles of silver to moles of electrons. It's becoming Ag plus, okay? And we have 107.87 grams per mole. And the silver is going to become an Ag plus. So for every 1 mole of silver, it would release 1 mole of electrons. Okay? Moles of electrons. How about we keep going and change it to current? We could do it right here, because we could go moles of electrons to coulombs to charge, because we have Faraday's constant. So we know that there is 96,485 coulombs for every mole of electrons. So if I take 3.56 and I times that by the Faraday's constant, and I divide that by the molar mass of silver, this is my charge. So I have 3,184.26, etc. coulombs of charge. That's like my Q value. I also know that my amps are 2.5 amps. And current, amps, is charge per time unit in seconds. And we want to know that time unit. We want to know how long it would take. So time multiplied by current equals charge. Time is equal to charge divided by current. And we know both of those things. We know the charge right here, and we know the current right there. So I'm going to take that charge, going to divide it by the current, and this is how many seconds. Take 1,273.7 seconds, 3 sig figs, 2 sig figs, so I'd go with 2 sig figs, and it could have said like in hours or anything like that, but they didn't, and so this would be, I said 2 sig figs, so 1,300 seconds. Okay, good. I want to keep today's video shorter, so I think we're going to end there, and then we'll just do some practice problems in class and get this unit all wrapped up. All right, thank you everyone for your hard work.